And here's the crazy part. Some of the most sophisticated AI systems out there aren't single monolithic brains. They're actually teams of AI working together. We're talking multi-agent systems, Srija.
Teams of AI, like actual digital committees making decisions. That sounds complicated. Is it really necessary? I always thought the goal was to build that one super intelligent AI that could solve everything.
That's the dream, right? But the reality is, many problems are just too complex for a single AI to handle efficiently. Think about something like autonomous driving. You could try to build one AI to process everything, the cameras, the radar, the maps, the other cars, the pedestrians, but that's a massive bottleneck.
Okay, I see your point. So instead, you break it down. Different AI agents handle different aspects of the problem. Like one agent focuses solely on pedestrian detection, another on lane keeping, and so on.
Exactly. And that's where the power of multi-agent systems comes in. Imagine trying to coordinate hundreds of deliveries in real time, like Uber Eats does. A single AI trying to optimize everything at once would be overwhelmed. The cost of getting it wrong? Late deliveries, frustrated customers, and drivers sitting idle.
So MASs are all about tackling complexity by dividing and conquering. But how do you actually design a system like that? What are the core concepts we need to wrap our heads around?
Great question. Let's break it down into three key areas. First, we have agent architecture, what makes up an individual agent. Second, we need to think about communication protocols. How do the agents talk to each other? And finally, we need to consider coordination mechanisms. How do we ensure they're all working towards the same goal?
Okay, let's start with agent architecture. Are we talking about completely independent AI models, or are they all sharing some underlying framework?
It depends on the application, but generally, each agent has its own perception module, sensors, data inputs, a decision-making module, the AI brain itself, and an action module, the thing the agent does. Think of a Netflix recommendation system. You could have one agent analyzing your viewing history, another looking at trending shows, and a third considering what your friends are watching. Each agent has its own model, its own data, its own specific task.
But how do they combine their insights? That leads us to your second point, communication protocols. How do these agents actually talk to each other? Is it just passing messages back and forth?
It can be as simple as that. Agents can communicate using a variety of protocols, from basic message passing to more sophisticated methods like shared blackboards or even auctions. Imagine a supply chain management system. One agent might represent a factory, another a warehouse, and another a retailer. They communicate by sending messages about inventory levels, demand forecasts, and shipping schedules.
So the factory agent says, "Hey, warehouse, I'm running low on widgets." And the warehouse agent responds, "Okay, I'll ship you some." But what if there are conflicting demands? What if multiple agents all need the same resource at the same time?
That's where the third key concept comes in, coordination mechanisms. This is about resolving conflicts and ensuring that the agents are all working towards a common goal. Think of traffic control. You have multiple autonomous vehicles trying to navigate the same roads. You need a system to prevent collisions and ensure smooth traffic flow. This could involve things like negotiation, voting, or even hierarchical control structures.
Hierarchical control, so like a central manager agent that tells everyone else what to do? Doesn't that defeat the purpose of having multiple agents in the first place? It sounds like you're just recreating the single brain bottleneck.
That's a valid point, and it's a common pitfall. The key is to find the right balance between centralized control and decentralized autonomy. Sometimes a hierarchical structure is the best approach, especially in situations where safety is critical. Think about a swarm of drones working together. You might have a lead drone that sets the overall mission, but the individual drones are still responsible for navigating obstacles and avoiding collisions.
Okay, that makes sense. So it's not about eliminating hierarchy altogether, but about using it judiciously. Give me another example.
Consider cloud infrastructure management. You have different agents responsible for provisioning resources, monitoring performance, and handling security. A central orchestrator like Kubernetes can coordinate these agents to ensure that the system is running smoothly and efficiently. However, each agent still has a degree of autonomy in how it performs its specific task.
But wait, doesn't that mean you're introducing a single point of failure? If the central orchestrator goes down, the whole system collapses.
You're thinking like an engineer, Srija, and that's exactly the right question to ask. That's why robust MAS design incorporates redundancy and fault tolerance. You might have multiple orchestrator agents or a mechanism for automatically electing a new leader if the current one fails. Think about how Cloudflare handles DDoS attacks. They have a distributed network of servers, each acting as an agent that can detect and mitigate attacks. If one server goes down, the others can pick up the slack.
Okay, I see. So it's not just about distributing the workload, but also about distributing the risk. But here's where it gets interesting. What about agents that compete with each other?
Ah, now you're talking. Competitive MASs are fascinating. Think of game-playing AI, like AlphaGo. It wasn't just one AI, it was a system of multiple agents, each exploring different strategies and learning from each other's mistakes. They essentially played themselves millions of times, refining their strategies until they were unbeatable.
So the agents are learning through adversarial training. That's brilliant. It's like having a built-in red team, constantly probing for weaknesses. But how do you ensure that the competition is productive? How do you prevent the agents from just sabotaging each other?
That's a critical design consideration. You need to define clear rules of engagement and rewards mechanisms that incentivize cooperation, even within a competitive environment. Think of financial markets. You have multiple trading agents competing to buy and sell stocks. They're all trying to make a profit, but they also need to follow regulations and avoid manipulating the market.
Okay, so it's about creating a framework that encourages healthy competition rather than destructive conflict. But what's the thing that most engineers get wrong when designing MASs? What's the counterintuitive insight that changes how you think about this?
It's this. Don't try to perfectly optimize each individual agent. The real power of MASs comes from the emergent behavior of the system as a whole. Focus on creating simple, robust agents and then let them interact. The complex, intelligent behavior will emerge organically. It's like ant colonies. Individual ants are not particularly intelligent, but the colony as a whole can solve incredibly complex problems.
So you're saying we should embrace chaos? Just throw a bunch of AI agents together and hope for the best?
Not exactly. You still need to design the system carefully, but don't get bogged down in trying to micromanage every detail. Focus on creating a flexible, adaptable system that can learn and evolve over time. Think about how OpenAI trains large language models. They don't explicitly program the models to perform specific tasks. Instead, they train them on massive amounts of data and let them learn the patterns and relationships on their own. The emergent behavior is often surprising and impressive.
Okay, I'm starting to see the light. So it's about designing for emergence rather than designing for perfection. What are some practical takeaways for engineers who want to start working with MASs? What should they do differently after listening to this?
3 things. First, start small. Don't try to build a massive, complex MAS right away. Begin with a simple problem and gradually add complexity as you learn. Second, experiment. MASs are inherently complex and unpredictable. Be prepared to try different approaches and see what works. And third, focus on communication. The key to a successful MAS is effective communication between the agents. Invest time in designing robust and efficient communication protocols. Think of it like building a team. Clear communication is essential for success.
So start small, experiment often, and communicate clearly. That's a great summary.
Absolutely. Remember, sometimes one AI brain isn't enough. The real magic happens when you bring multiple minds together.
I like that. The whole is greater than the sum of its parts, even when the parts are AI.